the factorial design that we learned before is the basis of DOE. Okay, normally you use factorial design to screen and to characterize. Normally when you perform the experiment, there are few steps. First you do screening, and then you do characterization, and then you do the what we call the optimization, and then you do confirmation. So any experiment, normally if your aim is to increase the production yield, to improve, to find the optimum of anything, normally this is the way how you perform the experiment lah. First you screen, and then you characterize, and then you optimize, and then you confirm. I think all of you got this, what we call this, I already share with you this thing, the what we call the flowchart in the handout that I provide with you. You can see in the chat. Let me check first. Okay, in the chat you can see the what we call this flowchart. So basically you can see here, this is general approach for DOE, how you do experiment under the DOE style. Okay, so let me make a little bit bigger. Okay, you start with screening, and then characterization, optimization, and confirmation. Okay. So you do screening. Basically, when you do screening, it's basically you want to find the most important effect. We have seen before how to calculate the effect, right? So to find which factor give the largest effects. Once you find this largest effect, you can what we call cast away all the trivial effect lah. I mean, that's something that not affected. For example, let's say you start with 10, and then after you screen, you found like 3 is the best. So 3 is contribute the largest effect. So you just focus on 3 lah. And then you can do characterization. Characterization here mean to find the interaction. Is this effect correlate with each other? Is this main effect correlate with each other? Is it, if I put this small, is this have some interaction between the other effect? So that's what does it mean by characterization. And here you can see the curvature here. What does it mean, curvature here, is that when you do the factorial, as we see before, you get something graph like this, right? You get something graph, something like this. The curvature mean is that when you add one point, let's say you test also, when you do factorial, you are basically testing at the low and also at the high level. When you add another point in the middle, let's say you have the point in the middle, and then the data shows that you get this point, response here. So let's say this is the response, this is the response, this is the factor of interest. Let's say you test also in the middle, and you found this data on the top. So in this case, you will see the actual the graph, it should be something like this, right? Something like, let me put the green, something like this. So you get the curvature. Normally when you do factorial design, the normal factorial design, you only what we call work at the low and high level. But you can also put the curvature. You can put you can ask the what we call this design, okay, I want to put the middle. The cost for that, you need to make more experiment lah. But if let's say you know that you want to optimize later on, so if you know that you want to optimize later on, then this response surface method is actually you put the point in the curvature lah. So the response surface method, the difference between response surface and factorial is that in your design space, like this, you putting the curvature in the middle. Let me put the black here in the middle. You have this, the vertex one to the green one, but also you put the point, mean that you test, you do some experiment in the middle. That's what does it mean by response surface method lah. You put another point, another curvature. You want to find what happened. And sometime also, let me make it bigger a little bit. Let me make it bigger so that you can see. Just give a general understanding lah. Okay, and sometimes you also want to see what happen if you perform experiment outside the design space here. So this axial point lah, you do axial point. So this is what we call central composite design. So it's under the RSM optimization. So let's say if you even if you don't put curvature on the factorial design, if let's say your SV, I mean let's say your boss, your supervisor, your lecturer ask your supervisor said that, okay, at the end of the day I want to optimize anyway. So I mean, even if you don't do curvature here, you will put curvature here. So you will get optimization later anyway. So but if let's say the budget is the what we call is the constraint, for example, you cannot run a lot of experiment, because if you go to response surface, then there are more runs. So you put the curvature here. Okay, at least you get some idea lah. Maybe your task, for example, if you do master or PhD, maybe your task is only want to find the rough idea where is the high and low. Then you can just do factorial. If let's say your task is to go hunt until the very end, then you need to do proper optimization lah. So that is the optimization part. You just add the curvature. Okay, because sometimes when you want to do factorial, you don't want to find curvature. Let's say sometimes there are no curvature at all. Most people they associate DOE with this beautiful graph with something like I don't know, maybe some of you familiar with DOE. They have like the like a 3D graph. They are like what we call bukit, no? Like it's like curvature graph lah. I mean, let me find here. Let me put here. Let me RSM response surface methodology. Let me put response surface methodology. Let's say I find the wait I slow pula. Okay, some of you might associate DOE with this image, this beautiful image like that, and hate if your image doesn't get something like this. But this is not the function of DOE. This is just one example. This, if you want to find optimization, that is fine. But if let's say you get something, the graph not like this, straight like that, that's still okay. Still not bad. This if you want to find the optimized version. But if you use a factorial design, then you cannot get something like this unless you put curvature. So in other words, it depends on what you want to do for DOE. If let's say you just want to find the interaction, this graph is much better lah. The one that the one that we see before is already enough to tell you there are interaction. If let's say your purpose is to find the whether this is affect this, what is the main effect, then this is enough. But if you want to hunt the optimize, then yes, you can go. You need to go for what we call the optimization part using RSM and so on. So it depends on what you do. Don't always associate DOE with this beautiful graph, because that is just one part. Okay, later on we will not cover here, but there are also the design of mixture design, which I will not cover here, but that's a little bit different. Okay, so DOE, when you think about DOE, don't think about this graph at all. I mean, that's one part of DOE only. You can have this graph. This also useful also. Okay, once you get the optimized version, you can do confirmation. Confirmation here, basically what? Basically, you validate your experiment. The software, when you do DOE using certain software, the software will give you at the end the predicted what happened if you change this, you change this, and then you give you the value. I will show you later on in practical tomorrow. But for time being, just give you the idea. This is the approach from top to the bottom. Okay, this is the approach of how you what we call to perform DOE overall step. Okay, so let's open. Let me cantik. Wait. Okay, this is general approach. Okay, cantik. Let me do like this. Okay, so how to perform DOE? Which software you use? Okay, so normally, as I said before, DOE is just a strategy. This is strategy. It's not a fixed thing lah. If you just want to characterize, just stop until here. But you can ease your task doing DOE by using a software lah. So I'm using this thing. So if you look here, you can go to statease.com. So let me open it full screen. So you can go to the statease.com. So I'm using Design Expert version 13. Okay, so you can find the trial error here. So this is one software that can do the DOE. If you have dedicated software, it's much easier lah, because it will help you from the design part until the analysis part. That's why we use software. You can do it manually, but yeah, that takes time. It's like doesn't compensate the less run that you get, but you need to compensate with like high time you need to analyze the design manually. So the software that people create is for a reason, to ease the flow lah, because there are a lot of statistical analysis. Because this Design Expert or whatever DOE software, the idea is to basically to design and to analyze, but the analyze is the statistical basis. That is the hard part lah. Not hard, I mean that is cumbersome to do manually. Okay, so this is the software. So let me open the software. Let me open. So I want to show you the example. Let me close this first. Okay, so I will show tomorrow. I will use this ni lah. I will show the example that the one by one, not one by one. I mean that I select a case study and I explain through this ni lah, especially for factorial and response surface. But I just want to show you something. Okay, what in this software? Okay, any software is doesn't matter, but more or less you get something like this lah. You can see here. If you close this, you can see there are three main what we call. You can see, right? Okay, there are three main design in this software. I call it DOE software lah. You have factorial, we have learned before. Response surface, we got some idea before, and mixture design. So there are three main design that you can do using this DOE software, whatever software you have. So you see the factorial. Under the factorial, there are a lot of design. Okay, let me open this thing. Okay, so you can see there are randomized, miscellaneous, split plot. You have under randomized 2-level, min run, multi-level, optimal. Under miscellaneous, you have Placket Berman and Taguchi, and split plot, and so on. Under response surface, you have what? You have this randomized. Let me open first. Okay, you have this randomized, central composite, Benson, optimal, definitive screen, split plot, and so on. Under mixture, which we will not cover, you have also another design, simplex lattice screening, and so on. And you also have custom design, where you can create your own design lah, provided you know what design you use. If you look here, we are focusing only on factorial and response surface for this workshop. If you look at factorial and response surface, they are sort of like divided into two main category. Randomized here, randomized, and also split plot. Similar to the response surface, you have randomized and also you have split plot. Okay, the idea is this. Sometimes you can, you always want to randomize your design. Okay, but there are times that you cannot randomize your experiment. Okay, there are times you cannot randomize the experiment. If you cannot randomize your experiment, then you can use split plot lah. Split plot. I will discuss later what is basically the randomized and non-randomized design later on. But for time being, just understand that under this specific software, for the factorial, you have randomized and split plot. For response surface, you have randomized and split plot. Okay, let's go to the factorial. So you can see this colorful stuff. So this colorful stuff is basically just graphical interface to make your to ease your choosing the design that you want lah. Okay, let's see. First, before we go to this, let's see first about. Let's give some idea first. Let's say let me give some case study. Okay, let's say you want to grow some, let's say for example you found a new fungi that can degrade plastic. Let's say you have this fungi, this is not fungi, but let's say this fungi, they can just eat plastic. Let's say this is your bottle. Let's say you find the fungus that can eat this plastic, okay, and you found this particular fungus. Let's say this fungus, let me put so fungus, this is plastic, and you found this fungus, this particular fungus is very sensitive to the nutrient that to give to them. For example, if you want to grow this fungus in the shake flask, let's say you have the shake flask, and then you grow this fungus in the shake flask, you grow this thing, and then you have this thing, and then you found that this fungus very particular, okay. If you put A, nutrient A, let's say I put nutrient A, he will grow. But if you remove nutrient A, regardless any other thing, if you remove this, then the fungus will die. Okay, so you know now, what you know is that nutrient A is important. Okay, nutrient A is important. The factor, if we think about this, nutrient A we can say is a factors for the fungus to grow. So the response here, so if you see here, let's say the box there, the one that we see, the response is the growth rate. Let's say growth rate, and then let's say we want to see only the effect of nutrient to the growth rate. So you have this, what we call the factors, and let's say you have A, and you know this A, without A the fungus die. So in this case, if let's say you want to screen, you don't put A. Okay, because when you want to screen something, you want to screen, let's say you want to know what is the amount of what is the nutrient is needed for this fungus to grow. Of course, you don't, if you use nutrient A, the fungus grow, but it's only at the certain level, not fast lah. Maybe if you use this only, maybe it takes 2 to 3 months to grow. So it's too long for you lah, 2 to 3 months for to grow. But it will grow provided you give nutrient A. So you know that if you add another nutrient, then the growth rate will be increased lah. From the reading, you found that if you add more nutrient, then the more faster the fungus grow. It's like you get a full, the fungus get this full sort of like vitamin and nutrient that's needed to their growth. So you need to screen. So what you do, you want to improve the growth rate. You want to improve the growth rate by what? By finding another factors, another nutrient. So you can list the factors, maybe B, C, D, E, and so on lah, and so on. So because you already know that A is what we call A is already needed, meaning that A, without A the fungus will die, then you can sort of like say this A is not included in the design. If you look here, if you look at this, you can see there are known factors and the unknown factors. The unknown factors here in this case is B, C, D, E, F, and so on. The known factor is A. Okay, imagine A is a nutrient A, nutrient B, nutrient C, nutrient D, E, F, D, S, and so on. So you are basically, for known factors, you don't put in the screening design, because you already know if you don't put this A, then it will die somehow. I mean, let's say hypothetically, you know that without A, no matter what you put, then it will die. So this is known factor. So you don't put in the screening design. You just waste time. I mean, if you put A, you just waste time lah, because you increase the number of factor and consequently you increase the number of runs. So you just what we call test this whatever that is unknown lah. That is unknown factors. So now you get this thing. So don't bother to screen factors that are already known. Don't bother screen factors that are already known to affect your response. In this case, A. Okay, so you don't put A. But you put B, C, D, E, and so on. So how to find all these things? What is B, C, D, E? Is depend on your literature review lah. Your reading lah. Basically your reading or your experience, especially when you are in the company, is based on the experience, how to choose this and other factors. In this case, when we talk about this fungus, depend on the experience. So So in order to improve, to find this factor, one more thing, these factors, when you want to find the factors, you need to go broad, go broad, don't narrow. Okay, what I mean is this. Let's say you know, in order for this fungus to grow, you need like a carbon source, and then you know carbon source have something like glucose, fructose, and so on. But if you just use the simple carbon source, for example, let's say you use glucose, you use fructose, you use maltose or whatever lah, maltose. For those who are not know about this, just imagine this is just the food for the ni lah, for the, it's just sugar food lah. So this is quite narrow, this is quite narrow. You can put this glucose, fructose, and maltose as B, C, and D, but the probability for you to find it will greatly affect the growth rate. The difference in terms of effect will be so small because it's come from the very almost similar carbon source, glucose, maltose, fructose. It's much better for you to screen the factors. You screen broad, meaning that you use complex source, complex carbon source, and you also know for any living material, you don't need only carbon source, you need also other stuff like nitrogen source, phosphorus, and then also maybe the trace mineral, and so on lah, and so on. So if you want to screen, you screen this way. You start broad, okay? You don't just screen the very narrow factors. These narrow factors is okay when you want to do optimization, but you want to screen, you don't want to miss anything lah. So you try to broaden your, what we call, your class, okay? So, and to choose which one, as I said, based on your reading, your experience, and so on lah. You can ask also those who are, in this case, you can ask those who are expert in fungus growing. So maybe they can give you some advice, and then that will sort of like save you a lot of time rather than you find yourself what is the nutrient needed for this fungus grow. Okay, let's say you end up, let's say after you all this screening, you end up, let me make it bigger like this, much easier. Okay, let me make this thing like this, much bigger. Let's say now after you do all this thing, you end up with the 12 factors. 12 factors, okay? 12 factors. 12 nutrients lah. 12 nutrients. Let's say B, C, D, E, F, G, H, I, J, K. 1, 2, 3, 4, 5, K, L, M. 5, 10. Okay, 12 factors. You have B until M. Okay, let's say this factor that you want to do. So the idea now is you want to find from these 12 factors which one affect most lah. Affect most of this thing. So if you look at this design expert, okay, you can see this thing. If you look at this factorial design, so under regular factorial design, let me open this thing. So this is basically regular 2-level factorial design. Okay, 2-level factorial design, meaning that we learned before what is 2-level. So if let's say you have 12, okay, 12 run, and you want to find the few, you want to remove some from the 12. So what you do is you do screening. You want to remove something. Okay, you see the color here? The white mean the full. I mean that full design lah, full factorial, meaning that you do a full what you call full run lah. 2 to the power of 4 is 16. 2 to the power of 5 is 32. It's like that. We learned about this before, right? So whatever left here, the green, the yellow, and the red is basically the fractional design. Okay. So for screening, you go either the red and the yellow. Okay. If you see here, they are also say something here. So the green for characterization, but for the yellow is for screening. Okay. The red is for ruggedness testing. Okay. Let's talk about this thing. Okay, if you see here, there are numbers. They are like Latin words here. They are IV, 3, V, VII. So this is what we call resolution. Okay, The higher the resolution, the better. The higher the resolution, the better. So you see the rate is at 3, the third resolution only. Have the resolution of 3. So that is low resolution. And here you have yellow, higher resolution, and green is even higher resolution. The white is the ideal, means that you test all the combination. Okay, so for the screening, you go either the red or the yellow. But try to avoid as much as possible for this red resolution. What does it mean by red resolution? You can see here, red is for ruggedness testing. Ruggedness mean robust. What does it mean? That is that if let's say okay, let's say I put here, let's say you have red the red one, the red petak tu. So there is low resolution. So it's okay for ruggedness testing, or we call it robust lah. Robust. What does it mean by robust? Meaning that you cannot sort of like screen certain factor that may be robust mean what? Robust mean the response. Robust here mean respond. What we call remain unaffected by certain factor. Okay, even though the factor you know it can give the response lah. For example, like this. For example, let's say you have 20 factors. Let's say you have 20 factors. Let's say you have total 20 factors. And then 5 factors give five give high effect. We know about effect before. 5 give medium effect. And then 10 give low effect score lah. So when you use red or low resolution design, what happen is that it will only find this high effect. Okay, so this low effect, because it's low, normally you don't care lah, you want to remove anyway. But the problem now is this medium effect. Okay, so if you use this low resolution, it will not resolve this effect, meaning that you will miss this effect. They will tell you only 5 is important, but the five high effect, this 5 lah, this top one is the important. But maybe this 5 medium, the medium for you is important. So, but if you use this low resolution, then they will not resolve this 5. It just say 5. Only 5 is contribute to the response. The rest is not contribute. Even though in reality there are another 5 that is contribute to the response, but the contribution is medium, which is maybe for some of you is important. So that's what does it mean by ruggedness testing. So the red one is this. The problem with the red one is this. So when you do screening, you either use red one or you use the yellow one. Oh, the yellow tak ada. Let me yellow. The yellow. I mean this color is just ni lah. The color is just the graphical, just to make things easy lah. But basically the more easy way to think is that this is medium resolution lah. Medium resolution design lah. Still low lah, low resolution design lah. So what yellow did is that basically it will find this thing also. What yellow did is basically it will control C, and then let me copy here. Let me bring here. So what yellow did is that it will find this also, medium effect. Okay, it will find both effect, meaning that it will find the main effect lah, either high or medium. If you look at these two resolution, this low resolution thing, you can see that there are no interaction. So this screening, they don't resolve interaction. interaction, meaning that you know that DOE can find the interaction right. But in this case, when you do screening, you want to remove something, so you don't care about the interaction. You just want to find which factor give the highest effect. So that's why you don't care about the interaction. So when you use a screening design, you cannot find the interaction. Okay. So if you see here, this thing, so the yellow here, so this also low resolution lah, but still a resolution 4 and above lah. So you can see it's resolution 4. I mean the screening is resolution 4. Screening is resolution 4. Okay, so that's the thing. So you cannot find the interaction between if you use the rate and this thing. Okay, if you look here, what does it mean is that if you have this 4, let's say you have previously you have 12, right? I mean for the what we call for the fungus that we want to see this time, the fungus that you want to see here, we get 12 factors. So how to do? Go to here. Yes, too much. So factors. If you do full resolution, if you do full, they are not even there. They are too much. They are 1,000 something like that. We see before, if you do 10 factors, it's already 1,000 something. So it's too much for the design lah. I mean, it's impractical. That's why it doesn't include there. So if let's say you want to screen 12 factors, you can choose either this, the red here, or the yellow here. But as I said, try to avoid this, what we call this, the red one. Try to go either this way. If you look here, the higher the resolution you go, for example here, you have 3 choice, 64. So if I click here, you can see here, 128 run you need to perform in order, if you choose this design, you need to perform 128 design. If you go this, you get 64. If you go this, you get 32 run. So if let's say the 32 is still too much for you, then you can go other design like placket berman and so on, or minimum run. Okay, for example here, the lowest for the screening for the yellow part, you see there are 32 run. Okay, but if you go to the minimum run, you see here there are minimum run, and you click the minimum run screening. If let's say I put 12 here, 12, you see the run is 26, is less than 32. If you use full factorial, not fractional factorial, you have 32 run. But here, if you use minimum run resolution, you have 26 run. Mean that you cut 8 run. Okay, so you can read here. Only use minimum run screening design if you cannot afford the run required by blah 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 and so on. Meaning that if let's say the budget constraint and so on, time constraint, you can use this. You can use this thing instead of using this regular 2-level fractional 12 run. You have 32. Meaning that 12 factors, you have 32 run. So at least with this minimum run screen, you can run a little bit lower lah. If you want to go even lower, you can use this. As I said, you can use this thing lah. This the red one. You see 12 factors. You go to 12. And then go to rate, you can see you can do even lower, 16 only. But you need to pay the price lah. You cannot find the medium effect, like I said before. You need to pay. So this, which one you want to choose is up to you. You decide. You as an experimenter should decide. And also you can see here there are placket berman and Taguchi. Placket berman also same like this thing, like fractional factorial. It's not factorial anymore. It's different design, but it can give you even less. For example, placket berman, if let's say I put 12, so 11 let's say 11, so you have 12 run, even lower than the total run. But the problem with placket berman is it is too robust, too rugged, whatever the spelling. Anyway, it's too robust. Even though you have 12 run, you need to you see there are warning here, warning and so on. It's much better for you if let's say you have 12 factor to go to minimum run screen. If let's say you cannot afford the regular 2-level fractional factorial. Let's say if 32 is too much for you, let's say here 32 is too much for you, it's much better for you to go to minimum run screening design than placket Berman, because placket Berman, they are the problem with placket Berman is they even here you can see warning, no attempt is to make to optimize the alias. I mean, alias here is basically the same. Alias means same name, right? Meaning that you have A and B. If you use a placket Berman, if let's say they cannot sort of like distinguish between A and B, is it the same? Is it not the same? So that's what does it mean by alias lah. So the alias problem in placket Berman lah. So that's why here it said that they recommend you to use regular 2-level factorial design if possible. Regular 2-level. If this is not possible, then it's much better for you to use minimum run screening here. Why I tell you this? Because this is the beginning of your experiment. If you make mistake at the beginning, then you end up with wasting time, wasting resource, or even doesn't get the response that you want. So the way how you choose the first design is critical. Okay, so that is the way how you choose for the screening. Okay, so the idea for the screening is basically this. You want to find the what we call you want to screen trivial many and just to use the vital few. For example, let's say previously we have 12. We have 12. Let's say I put the color here, 12. And then after you screen, you found there are 6 give the largest effect. We learned about effect before, right? Largest effect. And then you choose that effect. So let's say after the screen, you get this 6 here. You get 6 here. And then 6 here. So let's say this, the green here. And then this, the blue here. So you can see the 6 here, this one, the one here, the 6 that is giving the very low effect, you can discard. So that is the purpose of screening. You don't want to care about the interaction yet. You just discard whatever you don't need. Okay? Because sometimes you put a lot of things, a lot of nutrient. For example, in the case of this, what we call in this fungus, if you have 12 nutrient, you need to buy 12 chemical. And chemical is expensive. So if you can cut half, then you can cut half of the cost. Most of the production in the world, I mean, the main bottleneck is the raw material. Whatever production, the main bottleneck normally the raw material. So you want to use the minimum material but still get the optimum result. So that's why in this case, when you screen, you just want to remove this. Don't care about that. Okay, and then you just focus on this 6. Once you got this 6 here, the 6 that is important, then now you can do characterization. Characterization, basically you want to find the word characterization in the DOE, meaning that you want to find the interaction. Okay, see whether this one factors interact with these factors and so on. Okay, so basically screening, the purpose is to remove the trivial many and to focus on the vital few. So the vital few go here. So the non-factor, as I said before, like the A1, the one that we discussed before, you know that it is a factor, so don't just don't care lah. I mean, you don't screen lah. You don't waste time screening. You just put in this thing, and then at the end, because you have A here, you plus 6 plus A, you get 6, 7 lah. Total you have 7 lah. To check the what we call the, let's say here, let me put here because 6. Okay, let's say here 7 lah. Let's say I put 7 here. Let's say put 7 here. Let's say 5 here. Let's say I put this green. And then let's say this. So total now you get, so no, here. This is, so total 5 plus this is one factor here. So you get 7. So 7 will go to this thing. 7 will go for the characterization. 7 but 6 lah. 6 will go to characterization. 6 will go to the characterization. So that's how you start the experiment DOE style lah. So characterization, if you look at this design expert table again, you can see also the green. Okay, the green is for characterization. The green is for characterization. If you look here, the green is for characterization. Meaning that if you use this, you can resolve the interaction. You can find the interaction. Okay. The white is the idea lah. The white is the idea. You test all the combination, but the problem with the white is that it's too much. I mean, normally if people say if you have 5 and above factors, you go to fractional. because if you use the full Factorial, the white one is too much for you. It's just it's not pay off lah. It's much better you do Factorial, still get result. So that's why people said if you have 5 and above, then go Factorial. Is much, you still get the result. So the green here, now we talk about characterization. The green, you see there are resolution there. As I said, the higher the resolution, the better. But they are priced for that. If you see here, we have 6, right? We have 6 here. Let's say we put here lah. You have 8. Let's say 8 factors. Let's say we have 8 factors. You have this 1 green and 2 green. So the top one here is low resolution. Okay. The bottom one, this is resolution number 5, V, and this is resolution number, I don't know, 7, I think. 7 or 8, not sure. So basically, if you use low resolution for the characterization, you see you have 64 run, you need to run. But if you higher resolution, you have 128. So the cost that you pay by running low resolution is that you maybe cannot get some interaction lah. But you still get the main interaction, but maybe the small interaction you don't get because you don't test everything. Okay, if you want to know everything, then you go this full lah. But if you go full, then you get 256 what we call 66 run, which is you test all possible combination. But most of the time it's not necessary also. It's just a waste of time. Okay, resource budget and depend on time ni lah. So let's say here, let's say we have let's say we have what? We have 6 here. 32. As I said before, if the 32 is too much for you, you just go to minimum run lah. But here you can see here, on the left here, you can see there are minimum run for characterize, minimum one for the screening. Okay, minimum run for screening and also characterize. If let's say you are in the characterization, you want to characterize, you don't do this thing lah. You don't go for screening part. You go to minimum run characterize. So here, if you use fractional Factorial for 6 factors, you need to conduct 32 run. But if you do this minimum run characterization, you see you have 22 run. So you have 10 experiment less. So that can save a lot of cost in terms of material, budget, time and so on. So you see there are 2 things, minimum run characterize and screening. There are 2 things, so 2 are different things. So go for this thing if you want to do characterization. So that is basically characterization. Okay. So let's go back. So this is what this color looks like lah. It's like the traffic light lah. The red don't go, the yellow okay, the green just go, the white is too ideal lah. So that's the what does it mean by this thing. Okay. So here this is what I call the center point. You can put the curvature. If you want to put the curvature, you add lah. You put the curvature, but when you add the curvature, when you add the center point, then the experiment will be higher lah. The number of run will be higher lah. So that's the idea. But you can put the center block in order to find the curvature. That's why in here you can see there are curvature or not. Okay, it depends on your experiment. If you don't want to find the curvature, if you want to find the interaction, don't need lah. Okay, and then you go, let's say you know whatever this thing, and then you think that okay, 6 you find the interaction and so on. Now I want to do optimization, and I want to do optimization for all 6. Let's say you want to perform all optimization for all 6. Let's say you think you found that this 6 is so important, so I want to do all optimization for this 6 factor. The problem is if you do 6, okay, let's go to the response surface. So this response surface, this is normally for what we call for optimization. If I put 6 here, 6 factors, you see the number of run you need to run. 86 run. That's a lot. Okay. If let's say 1 run it takes 1 month, then you like come on. It just this is 4 years, 3, 4, 5 years like that to finish this thing. Okay. So it's too much for you. It's too much too much for what we call this. So that's why you have also box Benson and so on. So you see 6 run, 54 run, still a lot, still a lot lah. So that's why in this case what you will do is basically you need to decide which one from the 6 is the most super duper important. So you cannot run. Normally when you try to optimize, you don't optimize 6 lah. Normally the people optimize 4, like that is okay lah. Because when you do optimization, you need to remember, when you do optimization, you will add the center point. Not only that, you also add this thing, the axial point, meaning that your design will have a lot of run. So if you do 6, like we see before, it's 82 run. It's too much. So that's why it's much better for you to just do like best guess, which one is the highest effect. You need to sort of like, okay, I cannot do 6, then you just say, oh, I want to just do 4 only. So if you do 4, if you go this what we call, let's say, central composite, if you do 4, you will do only 30 run, which is manageable lah. Normally 30 run is manageable, what we call manageable. Okay, so what is the advantage of using this optimization? Because here, when you do optimization here, you will get sort of like the either graphical, what we call, in terms of contour, you get some contour, and also 3D plot, 3D, what we call, 3D maps, like that. This the one that you see here lah. This one, the contour. So you can see from the glance that okay, there are some optimum region and so on. But for me, the most interesting part for this optimization is numerical part, because this allow you to find the sweet spot. What I mean by this is this. What does it mean by sweet spot? Normally, when you try to do experiment, you have response. You have factors, you have response, and then you have the noise here, like noise, and then factors. The response here, when you want to put in the design software, whatever, you can test one response or multiple response. Okay, if let's say in case of this, what we call, in case of this fungus here, let's say the response that you choose is apart from this growth rate, you want to also see the cost. I mean the cost of running the experiment. So you have two response. So now when you have two response, even though you can increase this growth rate, normally you also associated with the increased cost. So no matter how good is your yield, if you are doing in the company or in the factory, then the management will say, oh, the cost is too much, it's too high. So regardless you have a high yield, so I will not commercialize this thing. So the company will say like that lah. So now finding the sweet spot is basically finding how these two respond. I mean, to find a compromise between two respond. Maybe you can reduce a cost a little bit, and you get sort of like you still get some improvement in growth rate, but not as high as theoretical maximum. But you still get improvement. But you can, but by doing that, you have this reduced cost. So you find the sweet spot between this thing. So numerical, for example, where is the thing? This numerical, the numerical analysis allow you to do that. You can set, okay, I want the cost this way. I want the yield this much only, not much higher. So I want this, the yield is only here, and the cost will be reduced a little bit here. So you get the sweet spot. So that can be done under this optimization lah, under RSM. We will talk in the next tomorrow. And then lastly, after you do all this thing, after you find the sweet spot and so on, the last thing is do confirmation, because the design will give some value, some prediction. If you change this, you get this. So confirmation meaning that you try to validate that. Okay, if let's say whatever you try to validate confirm the predicted, meaning that when you run the predicted version of the run, and then you get your observed value is almost similar to that predicted version, then you can say that model is good lah. So you can confirm lah. I mean, you just confirm whether whatever your analysis is correct or not. I mean, the design, because not only the DOE not only help you this, it's all this screening, characterization, optimization. Yes, DOE can find, but also DOE can also do prediction. This is under analysis lah. Analysis. It give you some prediction. Okay, you know that the optimize is here, here, here. But DOE said, if you increase this a little bit, decrease this a little bit, then you get much higher yield or whatever. So this, the DOE give you will create this model, and then they will ask you, okay, in order to see this model is valid or not, you need to test the run. So if you test this run, if you put the value of this much, this value of this much, you will get this much. You run the experiment, and if let's say whatever predicted by the software is what you get from your observe, you can say the model that is predicted by given by the DOE is valid. So that you get even higher yield or even lower cost than whatever you observe data during the experimentation step lah. So that is another advantage of DOE. It predict something. You can predict something also. So if let's say you confirm yes, then celebrate lah. If no, then you need to it's just prediction. I mean, sometimes the model, you need to change the model lah, because you can change the model. I mean, the software will give you the model, use this model, but let's say it doesn't give you don't get whatever is predict, then meaning that the model is something wrong with the model lah. So you need to back up lah. So DOE is more like a strategy. If you look here, DOE is more like a strategy rather than the fixed template.